So today we're gonna kind of continue down our journey of LQR and try to figure out some of the more nitty-gritty details. We're gonna do a bunch of physics and some calculus and so on. So we're just gonna go pretty slowly through the math and just stop me wherever. Small class, so we can go super slow. Yeah. Great. So we're gonna start with a little recap, and then we'll start working through how to solve LQR problems. Right? So where we are in the classes, we covered PID control, pure pursuit. We touched on optimal control in LQR, but we just kind of touched on it. So we'll recap that and discuss how to solve LQR problems and how to make them more general today. Right? Some logistics. Homework 2 is due today, actually. That's not tomorrow. But the cars can be demoed by Wednesday. So if you're not able to make it, find some time before Wednesday. We'll try to have paper readings for all the groups out by tomorrow. And homework 3 is almost done. It should be out tomorrow. You'll have like 10 days or so to do it. And it's relatively easy compared to homework 2. Okay, any questions about logistics? Okay, great. So the structure of today's lecture is we're going to start by trying to define what an LQR problem is, trying to take a classic problem and cast it as an LQR problem. Right? Then we will describe the solution to LQR problems, and then we'll talk about how we can go beyond LQR to nonlinear systems. Right? Okay, so let's start by recapping what we had before. We talked about bang-bang control, PID control, and pure pursuit. The issue with bang-bang control and PID control is that they're model agnostic. They don't take into account the dynamics of your system or your domain knowledge. And pure pursuit takes into account too much of your domain knowledge, right? It's like only moving in circular arcs, and so it only works for simplistic models. What we really want to do is we want to have something that works, for a more general class of models and for a more general class of cost functions. So you don't want to just, for instance, in PID or bang-bang, you're always trying to drive the error to a particular 0 point. You want to be able to solve general cost functions, and you want to be able to solve a broader class of models. Right? And you want to do so in a way that uses knowledge of the system, not just reactively. And so the motivation behind optimal control more generally and LQR specifically is to kind of overcome the limitations of these prior control methods. And so use model knowledge and be able to generalize the types of cost functions that you can solve, right? And so that's kind of the point here. And so we talked last time about how we can formulate control as an optimization problem. Let's just go to the definition. So we're saying that we have a system whose dynamics is F, right? So which means that if your state is XT, your action is UT, your system is going to evolve according to some dynamics F, right? So this could be your motion model that we described from lecture 3 or 4. It could be like a complex simulator. It could be this is where all your domain knowledge gets encoded, right? And that's how your system evolves. And then you have your cost function, which tells you what is desired of your control, right? Do you want to go to some position? Do you want to do it while not tilting more than some amount, while going some speed, while having some smoothness, right? And so typically all the things that you desire about your resulting behavior are encoded in your cost function. And the constraints of your system, like how the system can move, all go into the dynamics, right? So for instance, you have a car, your car can't just fly around the air and teleport. Right? So all of that is going to be encoded into F. Whereas your cost function C is going to be where do I want to go with what speed while obeying what laws, etc. And so that's kind of what a cost function C is and dynamics model F. Does that make sense? Okay, so the problem with this definition in its full generality is that it's too general. And so if everything is non-convex and nonlinear, it's going to be pretty hard to solve. It's pretty hard to solve analytically. And so instead, what we're going to do is we're going to start by choosing a more restricted class of systems. And that's what the LQR is, right? It's just like instantiating this problem with a particular choice of C and a particular choice of F. Yes? So in particular, an LQR system is something where your F is linear and your C is quadratic. Right? So your F is linear, as in your F is going to be AXT plus PUT, just like your Kalman filter, if you remember them. And your cost function is going to be quadratic. Right? So you can almost think of this as like x squared times q plus u squared times r. And these are the cost matrices Q and R, and your dynamics matrices A and B. And so your system is governed by these two equations. The top one is your dynamics, the bottom one is your cost. So if you go back to your previous equation, it's just saying cost is quadratic, F is linear. That's why it's called the linear quadratic regulator. Okay? Does it make sense? The general problem statement? Okay. So to kind of break down the LQR problem into matrix form, we can say that, let's say xt plus 1 is your state. It's going to be an n by 1 vector, right? Xt is going to be an n by 1 vector as well. And let's say your action is a different dimension, right? That's it's an m by 1 vector. And so you're going to have xt plus 1, which is n by 1 vector, is equal to a times xt. A is going to be dimension n by n. So that when you multiply n by n 1, you get n by 1. Right? And then BUT is going to be n by n. So that when you multiply it by n by 1, you get n by 1. And you sum up two n by 1 numbers to get n by 1. Okay? So nothing fancy here. It's just saying that your system is linear. By that? Okay. So let's try to work out how we can model a system like an inverted pendulum as a linear system, right? So last time we had started working through the inverted pendulum, but we got a little short on time. So the inverted pendulum is a system where you're gonna have you're gonna have like this ball and a rod, right? And then you're gonna apply some torque to your system, right? So your torque is going to be applied to the hinge joint at the base, and you're trying to like figure out how to balance your system in the presence of gravity and other things like that, right? And so the force is applied on your system, and there's going to be a tau, right? There's going to be a tau, and there's going to be a gravity, right? And this is going to be like a rigid rod. It's a rigid rod with a ball at the end. The ball has mass m. There's going to be gravity, and there's going to be torque at the hinge joint, right? Those are the forces on your system. Okay. Now let's think about, if you have torque, you can say torque is equal to the moment of inertia times the rotational acceleration, right? It's like F is equal to ma, tau is equal to I alpha. Now, in this case, let's think about alpha as like theta double dot, right? It's the second derivative of theta. It's only a rotating system, right? So alpha is like theta double dot. And or the moment of inertia is going to be ml squared. Right? So you're going to have ml squared, which is the moment of inertia. And your rotational acceleration is going to be theta double dot, right? Just by definition. Acceleration is the second derivative of position, right? Okay. So the right-hand side is ml squared times theta double dot. And the left-hand side is what is the torque on the system, right? So one way of thinking about it is let's take this force over here and let's take its component along this direction because it's perpendicular to the rod, right? So the force along that direction is going to be mg times sine theta, right? I'm just going to take the sine theta component when this angle is theta. Yes. And you want torque, so you're going to multiply it times L, right? Because that's the distance at which the torque is applied. And then you're going to say you also have torque, which is applied at the base of the system, right? Something that just applies torque to the base. So now you're going to have mg sine theta times L plus torque is equal to ml squared times theta double dot. Make sense? That's your equations of motion here, just from like basic physics. Okay. Now, you can like divide both sides by ml squared to get g over L sine theta plus tau over ml squared equals theta double dot. Yes? Okay. And now the nice thing about physics is you can approximate things all over, right? So what we're going to do is when theta is small, sine theta is approximately equal to theta. Yeah. And so you can write out this equation as g by L theta plus tau over ml squared equal to theta double dot. Yes. Everyone with me so far? That's just the equations of motion of your system, right? Any questions? Okay. So we can typeset it, right? And say theta double dot is equal to g by L theta plus tau ml squared, right? Now, if theta double dot is equal to this thing, that means that d of theta dot by dt is equal to g by L theta plus tau over ml squared, right? Yes? Which means that theta, like if you write out the definition of the derivative, right? You can say that theta dot t plus 1 minus theta dot t divided by some delta t, right? That's the definition of the derivative, is equal to g by L theta plus tau over ml squared. Yes? Which means that you can write out theta t plus 1 dot as theta t dot plus g by L theta delta t plus tau over ml squared delta t. Yes? Okay, so that is the first equation, right? Everyone buy that? Okay. And the second equation is just saying that, you know, d theta by dt is equal to theta t dot, right? Just the definition of the derivative, which means that theta t plus 1 minus theta t by delta t is equal to theta t dot, right? Which implies that theta t plus 1 is equal to theta t plus theta t dot times delta t, right? That's equation 2. So this is your equation 1, this one right here, and this is your equation 2. Yeah, so that's defining how your system evolves. You defined all of this in continuous time, right? You define them in derivatives, and now you just want to see how your system evolves numerically. And so you can just use the definition of the derivative to say that the velocity, rotational velocity at t plus 1 is equal to the rotational velocity of t plus g theta over L delta t plus tau over ml squared delta t, right? And similarly, you can say your position at t plus 1 is equal to the position at t plus the velocity times delta t. Right? Those are your two equations. Now, what we're going to do is we're just going to rewrite these in matrix form, and then it's going to magically look like LQR. Yeah. So everyone follow this before I get rid of it from the board? Any questions? Okay. So let's unpack this a little bit. Right? So what we're going to do is we're going to set the state of our system to a combination of the position and the velocity. Right? So it's a vector valued state. The state is the position and the velocity of the system. So in most robotic systems, you always want to have the state be position and velocity when you're doing second order. So you're saying, okay, you're going to have position and velocity. And now, if you just expand these matrix equations, you're going to get exactly the same two equations that we had before, right? So let's work through it real quickly. So the first, if you just do matrix multiply, the first row becomes theta t plus 1 is equal to 1 times theta t plus delta t times theta t dot plus 0 times tau over ml squared, right? Which means that theta t plus 1 is equal to theta t plus theta t dot delta t. Same as the last equation we had, right? So that's the first row. And the second row says theta t plus 1 dot is equal to g over L delta t times theta t dot, or times theta t, sorry, plus theta t dot times 1 plus tau over ml squared delta t. Yes? Just expanding this matrix multiply. And that's your, if you look at that carefully, that's the first equation we had, right? And so all we've said is we worked out things from physics, and then you can express the evolution of your system as when your state is the position and velocity as this linear equation, right? So it's linear if you choose your state as theta t plus 1 and theta dot t plus 1, and your action as tau over ml squared, right? Then you can write this as a linear system. So you can always write it as xt plus 1 is equal to axt plus but when a is this thing and b is this thing, right? And it passes our sanity checks because n here is 2 M is 1, and this is, you know, a 2 by 2 matrix, and this is a 2 by 1 matrix. So like passes all our sanity checks. It's a linear system. And the main thing to notice that I did here, which is a little bit suspicious, and we'll get back to it, is I made this approximation that sine theta is approximate. And so I like linearized the system. And that's a little suspicious. But for most systems, you can do some version of this to make it work. You can do some version of linearization to make it work. But this is kind of the explanation of why this is a linear system. We buy that? Yes? Okay. Great. So the second part of the LQR system, besides the linear dynamics, is the cost, right? And so the cost here is going to be a scalar, lossless scalar, because you want to optimize it. So the scalar is going to be xt transpose times q times xt plus ut transpose times r times t, right? And the dimensions here is going to be xt transpose is 1 over n, q is n over n, and xt is n over 1. So it's 1 by 1, it's a scalar. And ut is going to be 1 over m, r is going to be m over m, ut is going to be m over 1. Right? And so the way you can think about it is that the coefficients in q and r are going to decide which elements of the state are important. Right? So imagine that we had you know, something like, you know, a cost that looks like this for our choice of state in our invert pendulum. So your state is theta t dot, right? It's like the choice of these coefficients determine how much you care about position and how much you care about velocity. Right? So for instance, I like bump this thing up like really large, right? And I bump this thing down to be really small. That means that my cost cares a lot more about position than it cares about velocity. And so what it allows you to do is it allows you to prioritize errors between different releases. And so this allows you to express general cost functions. There's two other conditions on cost functions that we're going to have. The first is that there's this property called positive semi-definite, right? PST. How many of you know what that means? Okay, so what a PST matrix is saying is that it's like basically the matrix version of positive, right? So it's saying that basically the sign from positive semi-definite is right here. And it's saying that if you have a matrix Q and you multiply it by any vector Z, right, that's not 0, then the Z transpose QZ is going to be positive, right? Or this is actually positive definite, not positive semi-definite. But if Z is not equal to 0, that means that it's a positive. If you look at it in the scalar version, this means that the scaling coefficient is positive. Right? This is just the matrix version of positive. Make sense? And you're going to have a similar condition on both Q and on R. Right? And so you can think of like Q as like deciding how much to focus on different positions of different parts of the state space. And U is like penalizing things like don't apply huge amounts of torque, or like trying to like, you often call it a control cost, so you don't want to apply huge forces and stuff like that for like, you know, real systems. You want to keep everything under control. So yeah, most LQR systems will have some combination. Yes. And we'll try to instantiate this more concretely, but you can apply basically the same costs to the inverted pendulum systems. Okay, so what have we done so far? We've defined this inverted pendulum problem. Just to go back, we've shown that it's under some approximations, it's linear dynamics, and then you can choose some set of cost functions that are quadratic, right? Which means that it's like squared. Like an easy way of thinking about this is that this cost is minimized when x is 0, right? And in this system for inverted pendulum, x being 0 means that you're like upright at rest, right? Because your theta t is going to be 0, your theta t dot is going to be 0. So the state that optimally, like the state that minimizes the cost is the zeros. Does that make sense? You can also modify the system so that the state that minimizes not 0, but don't worry about that. In this system, it intuitively makes sense that the inverted pendulum, you want it to be upright and not moving. Okay. Do we feel pretty clear and confident about what an LQR system is, right? So the definition of an LQR system is something where dynamics are linear, cost is quadratic, and we want to solve like an optimal control problem, which looks something like this, where C is quadratic and F is linear. Okay, do we feel prepared to solve it? No? Okay. Are there questions about the system and like the problem formulation that we can answer before we get into the solution? Yes. Yes. Oh, that's what Q is, right? So yeah, you just pick Q. It's like something that the user specifies. Okay. So it's like the user can specify they actually really care about position and not about velocity, and they will like choose a Q where the first term is really high. Or they say I care equally about them, and so then they'll choose a term where these are, right? And so it's like a choice of this. Like typically in optimal control problem, the cost function is given to you.
And the
Yeah, just saying that the cost is always going to be positive. That's it. So you want to minimize it, meaning minimum cost is 0.
I realize that I think like I might run into homework territory, but I'm kind of just like not sure how you think this and think about it in our car context. But I feel like I get it in terms of.
So in your car, you already defined the motion model, right? So you had like xt plus 1 is something and yt plus 1 is something and theta t plus 1. The problem with that is that it's not necessarily linear. And so the way you need to get it to be linear is you're going to use a Taylor approximation. So it's not actually on your homework because it's a little too complicated, but if you wanted to use LQR for your car, you would like take those equations with those sines and cosines and everything, and then like linearize them with a Taylor approximation. So it does. Okay. Do we feel more clear about the problem definition? So C is given to you by a user, and F is like a property of your system, right? So it's like F is coming from physics, C is coming from the user, and you're trying to find the sequence of actions, right, that minimize the cumulative cost from one. Okay, so let's kind of think about how to solve it. Let's get through this. So if you want to think about how to solve it, we're just going to go start with intuition, and then we're going to go through this step by step, right? The key idea behind solving for LQR is just dynamic programming. Okay? So we're just going to go step by step and try to use dynamic programming, reuse the same recursive procedure over and over. And the key to like deriving LQR is start from the end, start from the last time step and go backwards. Right? And so you want to start at the last time step, -1 or p, and then just go backwards. So, schematically, what this suggests is that let's start by considering a problem where you have one time step to go. Right? It's like a horizon 1 problem. Like you are somewhere in the world and you have one time step. Like what would you do? Right? That's the last time step. And then you find the solution to that, and then we'll reuse the solution to that in a problem where we have 2 time steps. And then we find the solution to that, and then we use that in a problem that has 3 time steps and repeat. Right? And so the trick is we're going to start very simple from the end, and we're just going to keep reusing solutions as we go back. And so essentially, you're going to try and find solutions for the last time step when you have 1 time step to go, right? Then you're going to try and use that in solutions for 2 time steps to go, and you're going to try and use that in solutions for 3 time steps to go, and so. Intuition makes sense. So it's like the same as any dynamic programming knapsack, and this is like basically the same problem, right? We're just going to have a particular choice of like optimization per types. And so we'll start at the last steps and go back. Okay, so going back to our like definition of the problem, this was the system. It's linear. There's the cost function that's quadratic. You want to choose the actions that minimize the cumulative cost subject to the dynamics, right? And so the solution to this is often called the Bellman equation. Right? The Bellman equation also shows up in reinforcement learning. It shows up in optimal control. It's like this Bellman dude is amazing. So it's basically the same idea. So all we're going to derive in reinforcement learning is going to be very similar to this, right? So let's kind of work through this one at a time. And so let's define this entity J, right? And J is basically the sum of costs in the future, right? And so what you're going to say is that your minimum cost, so J is going to be your sum of costs in the future, and J star is going to be the optimum of that, right? So your minimum cost starting from XT is going to be your immediate cost plus your future cost, right? So you can think of it as sorry. Your cost at a particular, like the best you can do at a particular time step, right, is basically minimize the current cost, right? So this is the cost at the current time step plus the cost in the future, right? And so you can say that this forms this recursion where the minimum cost at a particular time step is the minimum of the cost at that time step, right? Plus the minimum cost in the future, right? And that's what that's all that the Bellman equation is. It's saying the cost now is equal to the minimum of the immediate cost plus the future cost. And importantly, you're not minimizing just over this, you're minimizing over the sum of these, right? And U doesn't just affect the immediate cost, U also affects the future state. And because it affects the future state, it's going to affect the future cost. Yes? Yeah. It's currently if you add noise, everything's just going to become an expectation, but right now, in the first version of LQR, it'll be deterministic. Okay, so this is just the intuition behind the Bellman equation, right? Let's try and like work through starting from the back and going backwards, right? So let's define this entity J sub I. Sorry. Let's define this entity J sub I, which is saying what is the cost from time step from state X if I have I time steps to go, right? And I'm acting optimally in the future. So J sub I of X, right, is going to be essentially min U of XT X transpose QX plus U transpose RU plus J I minus 1 of X, XT plus 1, right? So if we had to define this by time steps, right, it's just saying that the subscript is just saying how many time steps you have to go. And so let's start by just thinking about the simplest case, which is just you have 0 time steps to go. You're the last possible time step, right? If you're at the last possible time step, there's no future cost. You're at the end of the road, right? If you're end of the road, the only cost, this is just equal to your like C of XT UT, right? And so this can be your J0 is just immediate cost, no future cost, okay? Now, if this is your minimum cost, if this is your J naught, like what is the solution to this problem? We've said that, Q is positive, definite, and R is positive, definite, right? And they're only equal to 0 if X is equal to, like, this thing is only equal to 0 if X is equal to 0. This thing is only equal to 0 if U is equal to 0, right? So if I was to, like, find the minimum of this equation, what is 0, right? That's it. So the minimum of this equation is at U equal to 0, right? Right? Just because the definition of the problem, you have no time steps to go. If you're at X, the best thing you can do is apply no action, right? And intuitively, this makes sense because it's like, I'm at X, fuck it, I can't do anything. I might as well not apply any, controls. So, so the trick here is that this solution to this thing is at U equal to 0, which means that this whole thing will reduce to X transpose QX. Right? So it's saying that at the last time step, let's say you're at some state X, the cost at that state X is going to be X transpose QX because the best thing you can do is apply action 0. Does that make sense? Okay, so that is the last time step, right? So if we typeset that, we can say U is going to be equal to 0. U is equal to 0 plugged in, second term goes to 0. Your cost is just equal to X transpose Qx. Yes. Now, just for the sake of like making the recursion work, let's define this like P0, where the subscript determines how many time steps you have to go. Let's just call P0 equal to Q. Okay. And the reason this is going to be important is across all the time steps, we're just going to say that Ji of X is going to be equal to like X transpose some Pi of X. And we're going to show a recursion to compute what P at any I is going to be. So we've done the base case, right? We've done like the last time step, U is 0, and you just incur cost according to X transpose QX. Okay. Any questions here? Does it make sense? Yes? Okay. So we've done the last time step. And so intuitively, it's saying that, of course, that cost is going to be minimized when X is equal to 0, right? But if X is not equal to 0, then you incur cost, which is for that. Okay, so now when let's consider one time step to go, right? So that means you can act now and you can act one step in the future. And now what you want to do is you want to compute the solution to this problem, J1 of X, right? So we've defined J0 of X from the last time step, and now we want to solve for J1 of X, right? And so you can say J1 of X is saying you're at some state X, you can apply one action U, right? And then you now are in the problem where you have one step to go. So J1 of X had, 2 steps to go. And sorry. So J1 of X has 2 steps to go. So this is like the second last action, this one right here. And then it says you take the second last action, the system transitions, and then you act optimally again, right? So if you want to act optimally at every step. So you take an action, and then you assume you're going to act optimally at every step in the future, right? So if you act optimally at every step in the future, this problem becomes the same as this problem, right? So this is just the same as the Bellman equation. It's saying that the cost to go with one time step to go, right, is going to be you take an action, your state transitions according to the dynamics. You have linear dynamics. So you were previously at state X, you took action U. So your state transition to AX plus BU, right? And then you act optimally at AX plus BU if you had 0 time steps. Right? And that basically becomes the J naught problem, but just at the state AX plus B. Okay, this is important because at the second last time step, your U controls both your current cost and it controls your future cost, right? Because it controls your future cost because it determines what state you're going to be. So it's like my U currently is going to be penalized some amount and it's going to control where I go. Right? So U shows up in both here and so what we want to do in this step is we've defined the cost to go, J1, and we want to minimize this objective. Yes? Okay. So let's try and minimize this objective, right? So let's do it on the whiteboard. Oh no. Am I stuck again? Yikes. Sorry, iPad issues, but okay, hopefully we can work with it. Okay, so we want to minimize this objective. We defined J naught previously, right? What is J naught? So we've defined J naught of X, right? So can someone tell me what is J naught? We just defined it. X transpose QX, right? Or like, we're going to call it P naught for a second, right? So it's going to be just like X transpose P naught of X. Yeah. That's what J naught is going to be. So now let's just substitute that definition into here, right? So this whole objective, J1 of X becomes min U of X transpose QX plus U transpose RU plus J naught of X, but X here is going to be AX plus BU because you've transitioned one step in the future, right? So it's going to be AX plus BU transpose B naught AX plus BU, right? You can just think of this as like substituting ax plus bu for x here, for x here, right? So all we've done here is we've substituted the definition of J0, right, into the definition of J, right? And we've just like, it's a J0 the function, you're just going to call the function instead of x, you're going to call it with ax plus b. That's, do we buy that? Yes, no, maybe? Okay, so we started with, one step to go. And we said, hey, we're gonna say one step to go is the quadratic cost of the current time step, plus the quadratic control cost of the current time step, plus the cost in the future. And this is what we call cost to go. And so cost to go is gonna be ax plus bu transpose p naught, ax plus b. Okay. Now we want to solve this problem, right? You have this minimization over this, like this thingy. How do we solve it? Like, how do we solve a minimization problem? Derivative set to zero. They're going to take the derivative and set it to zero. So in this case, we're going to take this thingy. We're going to take its derivative and set it to zero. And that's going to give us the minimum u, right? Whenever you have a function, take the derivative, set it to zero. Now let's work through what this is going to be, right? So x does not depend on u. Derivative is zero, right? Derivative is zero. U transpose RU. What's the derivative with respect to u? 2RU, right? Okay, so it's going to be 2RU. And then the next term, we're just going to use chain rule, right? So you can almost think of this as like derivative of this thingy, whatever, by ax plus bu times the derivative of ax plus bu with respect to u. Yes, this chain rule. Okay, so this thingy is a quadratic, right? So it's a quadratic in terms of ax plus bu, and this thing is linear in terms of u, right? And so you can write this whole thing as 2RU plus 2 times ax plus bu p naught times b. I think there's a transpose I'm missing somewhere, but times b. I think, sorry, 1 second. I think this one goes over here. So all we did here is we applied the chain rule, and this is going to be 2 times b transpose b naught is equal to 0, right? So we took the derivative. The derivative is going to be gotten by chain rule. This is a quadratic. This is linear. Linear, you can think of as giving you a b. This is, you can think of as giving you 2ax plus bu times p naught, right? And so this is going to be the combination of them, right? So let's slow down here. So what we've done is we have this sum of 3 terms. Okay, sum of 3 terms. You took the derivative with respect to u. First term was 0. Second term was 2RU. This third term, you apply the chain rule, right? The chain rule is first on a quadratic, the second on a linear term. This is 2RU. And this is the product of the thing from a quadratic and a linear term. Yes? Okay. I might have made a small mistake on the transposes, but I think we can. Everyone with me so far? So all we did is we took this thing, we took its derivative, right? Okay, so let's go to the next slide, right? So if we just typeset it, right? I got it right. Great. So the first term is coming from the derivative of the quadratic, and the second term is coming from the derivative of the cost to go, just using chain rule. We have a quadratic and a linear. You can just work through this again, but intuitively, you just want to take it as taking the derivative. And then you want to set it to 0 to solve for u, right? So if you set it to 0, you just basically move, this thing, you separate this thing out into this term and this term. You can write this as 2RU plus 2B transpose B naught. Sorry. BU is equal to minus 2B transpose B naught AX, right? I just like expanded this and grouped the U's together, right? And then you can cancel off all the 2's, and you can say U is equal to R plus B transpose P naught P inverse times P transpose P naught A X. Yes? So all we did is we took the derivatives, we give you that term, you group the U's together, and then you like multiply both sides by the inverse together. Now, from all your like sagely wisdom that you've collected in CSE 478, like does this remind you of anything else? Like have you seen like a weird thing like this before? Kind of ish. Like think through all of the strange lectures we've covered, like which one, what does it remind you of a little bit? It's basically the same as a Kalman filter. So you think of the Kalman filter, right? It's like you can think of you as like fancy Kalman game thing, this K term, this messy thing. It's like almost exactly the same as this. And we'll go into more detail about it, but basically it's like very similar to a Kalman filter. And really the Kalman filter is the dual of LQR. And so they're like they're like essentially the same thing. Just like solving different problems, but the equations are the same. Okay. Not that important, but I think it's like quite cool. Okay, so what we've done here, we've solved for U. So we've solved for U. So one thing you want to notice here is that U is actually just linear in X, right? So you can almost write U as, or you can write U as KX, right? Where K, the linear term, is going to be equal to like this thing, right? And U is KX, so that's why it's like a linear feedback controller. So U, the action is computed by taking your X and multiplying it by this like linear K. Right? And now we're gonna compute two different things, right? Like the first one is we said U is equal to KX, right? So we've agreed that U is equal to KX. This is great. Where K is equal to like this thingy, right? And then if you plug U back into this equation over here, right? I'm going to skip the exact derivation for the sake of time, but you can show that the cost is quadratic with the quadratic coefficient as this thing. Like you can almost just think of it as like, take this thing and substitute it in here and here and here and here, right? So under the definition of K, which is minus R plus B transpose B naught B inverse B transpose B naught AX, or sorry, no, like that's the definition of K, right? The nice thing now is that U is equal to a linear function of X, and the cost is a quadratic function of X, right? So you can write this as your Ki, right? Or K1 in this case. And then you can say that your P1 is a quadratic function, or your cost one is a quadratic function, X transpose P1X, where P1 is basically going to be this. It comes from the fact that your P's and P's and Q's are, or your things are positive. It's a good question. Okay, so what we're going to do is we're just going to notice that we've gone from 0 time steps to go to 1 time step to go, right? And we've like expressed everything at time step with 1 time step to go in terms of the 0 time step to go, right? So as in at 0 time steps to go, you had action as 0, and the cost was X transpose P0 of X, where the P0 was Q, right? And now what we've done is we've got as a 1 time step to go, where we've said you have a linear feedback controller, which can be expressed in terms of like P naught, right? Which is like, take 1 step in the future. And then you've expressed the cost as quadratic in terms of P1, and P1 can be computed using the previously computed P naught, right? And so the point is now you can just like apply a recursion on this, right? So if you turn it into a recursion, what it says is that you have this K term, which is your gain. That's what we call your gain, usually your K. And your P is like your quadratic cost term. And so your gain is in terms of your quadratic cost term 1 step in the future, right? And your your cost term at the current time step is in terms of your current gain and your quadratic cost term one step in the future, right? So if you start at the end and just go backwards, you can just keep applying the system of linear equations in order to keep computing your gains AI and your quadratic cost terms PI, right? So think of it this way, you just start at the end, last time step action is 0, and the cost is X transpose QX, right? And you set that to your P0, and now you just go backwards in time, just continuously updating your KI and PI this way, right? So you compute at K1, what is K1 going to be in terms of P0? What is P1 going to be in terms of P0? Now you're going to repeat and do it in K2 in terms of P1 and P2 in terms of P1. And then you're going to repeat and repeat and repeat till you go all the way to the start of your system, right? So it's like essentially saying, try to be optimal at the last time step, try to be optimal at the second last time step, try to be optimal at the third last time step, and you can reuse everything. Does that make sense? Mechanistically, at least, we'll try to interpret this a little bit more if the guy doesn't break into the room. Okay, so the important things to remember here are that your optimal controller is linear X, right? And your optimal cost is quadratic X. And so you're gonna like just keep repeating these things over and over. So you can like implement an LQR system, something like this. Your base case, if your time to go is 0, is return your gain as 0, but your action is going to be 0, and return your P naught as Q. And then for every other step, you're going to express the gain and the quadratic cost in terms of the quadratic cost from the time whistle. Right? And this is going to give you a controller every step. So once you compute KIs and PIs, the way you're going to run your system is you're just going to keep running your system according to the rule U is equal to KX. Right? So you've computed, let's say your time step, 1, you've computed U1 is equal to K1X. Your time step 1, you're at some state X, you're going to apply U1 is equal to K1X. That's it, right? And you computed K1 to K the end of time, and then you play the world forward, right? So you compute this thing, and now when you're acting, you just act according to that feedback. Okay? And when your system is linear and quadratic, that gives you something that is optimal. Does it make sense? Okay, so let's see if I can kind of unpack this a little more intuitively. I find this quite a bit. This is called like the discrete algebraic equation, or DARE, right? And let's try and unpack what these terms mean, right? So I think maybe the easiest term to understand is this gain term, KI, right? And if we like connect it back to Kalman filtering, you can write it just like write the inversion as division, just the shorthand, right? You can write it as B transpose PI minus 1A, where the R plus B transpose PI minus 1 epsilon. For the sake of simplicity, let's just set A and B to identity, just for a simple case. And if we set A and B to identity, then this term just becomes PI minus 1 divided by R plus PI minus 1. Right? And so if you remember our like Kalman gain from Kalman filtering, right? This is telling you how much in Kalman filtering, it is how much you trust your sensor versus your belief, right? We had a trade-off between how much do you trust your sensor versus your belief. Here you have a trade-off between how much does the current cost matter. R is telling you how much does the current cost matter, and PI minus 1 is telling you how much does the future cost matter. Right? So if like R is ginormous, right? Then basically it's saying that like fuck the future, you just care about the now. And if R is huge, then say nobody cares about the future, just like minimize control, which means that you are going to apply U equal to 0. Right? And if R is really small, that means that don't care about the now, only care about getting to the right state in the future. Right? And so it's going to say you're going to try and act to get to 0 as fast as possible. And so you can think of your K term as like just trading off the cost of now versus the cost of the future. So that's how I find it intuitive to think about. And then secondly, the cost term again has a similar intuitive flavor, right? So the cost term, think of it as like that is your PI term, and then your cost is going to be hitting the PI term with an X on both sides, quadratic. Yeah. So your cost is going to be X transpose PI times X. Okay. So let's look at each of these terms one by one. So the first term is just going to be X transpose QX, right? So it's just the cost of the current state. It's like, that's where you are in the world. That's the cost you're going to get, right? So that's the current state cost. Not much you can do about it. The second term is the current action cost. So if you remember, our action cost is U transpose RU, right? But U is equal to KX, right? Which means that U transpose RU is now X transpose K R K X, right? So that is just this thing, is just this thing, right? So it's literally the control cost at your current time step when you're acting according to the feedback control, right? And then the last term is optimal cost in the future based on the dynamic, right? So the last term is saying you're gonna take one step and then you're gonna consider what the cost is going to be in the future. So intuitively, you can think of it as breaking down those three costs, and then you can think of your gains as coming by trading off your current cost and your future. Okay, that's it for now. Let me know if you have any questions. Thank you. And